it's already done.
Okay, then welcome everyone to our weekly colloquium of the Physics Institute of the UNAM in Cuernavaca in Mexico. Our guest today is János Török from the University of Technology and Economics in Budapest in Hungary. Let me say some few words about the vitae of Professor Török. So he did his PhD shared at the Budapest University of Technology and the University Paris Sud in France. Then he did various postdocs, some of them at the Weizmann Institute in Israel and at the Institute at the University of Duisburg in Germany. And I think since 2012 he is associate professor at the Budapest University of Technology and Economics. Yeah, his research interests are in granular materials, in rheology, effects of particle shape, fragmentation. Recently, he's also doing research on social networks, the formation of these networks, big data, and just to mention one award from the list of awards he earned is that he was awarded 2 times the Teaching Excellence Award at his university. And the curious thing with this is that this award is it is decided only by the students. So the students decide who is the best teacher at the university, and János won it 2 times. So I think
actually just the faculty. So it's
okay. It's just a okay. Okay. Then János, thank you very much for accepting our invitation and joining us today over at Zoom. And we are looking forward for your talk.
Thank you very much. And let me just share my screen. I think it's fine. Yeah. So thank you very much for the invitation. And I would like to present you some work that I did with Gábor, Douglas, and Ferenc together. And it appeared end of last year. And actually, this is my first paper that got me any media attention, and it's got already a lot of media attention. And you are proud of it, but I already tell people that sometimes when you get too much media attention, then even the Hungarian radio news reported that, but in these news there were only our names correct. So I really hope that you will enjoy it. So what I will talk about it is fragmentation problems and a way to understand it. And I think why we got some media attention was that due to this philosophical title that my boss Gábor Domonkos gave it. So it will be about Plato's cubes and natural geometry of fragmentation. And first of all, I won't start with an outline, but some kind of philosophical motivation about it. First of all, of course, the Platonic solids that were most probably discovered by Pythagoras. These are these 5 ones, the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. And, the thing was that Plato associated it to the elements, but a problem is that traditionally there are only 4 elements, the fire, the earth, the water, and the air, but there are 5 Platonic solids. So he had the same problem as in this movie, and he solved this problem by associating the 5th to the heaven. Yeah. So here are the Platonic solids. The tetrahedron is the fire because it's sharp. The octahedron is the air. And the cube, I would like to draw the attention because I will talk a lot about the cubes, is the earth. Because actually he had this idea, these are his words, that dirt crumbles and breaks. And this is actually, the cube is the only one that fills the space. So Plato, actually already Pythagoras found out that actually this is the only object with which you can fill the space. And I also like that in this Platonic view of the world, there is no hell, but just heaven. And the heaven is this dodecahedron because we have this 12 zodiac. I think that was the reason why he chose this one. And you know, when we had this idea, you will see why this cube is so important. About fragmentation, you can see here already the word break. And then something else came. Actually, it was not our mind. This was one of the news site. When the news site published our paper, they used this picture as a cover. And it is a picture from Minecraft. Most probably all of you know this game. And this game is composed of cubes, because actually this is the only one from which you can build up, fill a 3D object. And in this world, everything is made of cubes. So the whole world is created. Actually, you can see errors because the clouds shouldn't be cubes, because they should be icosahedron and octahedron and icosahedron combination or whatever. So now this is how this philosophy got into play. So some philosophers said the Earth is made of cube, and our question was he right? I mean, was Plato right, or is it completely wrong? Of course, when we think about, of course, it's completely wrong, because fire is not tetrahedron, and definitely water is not an icosahedron. But this can have some truth in it. And just a further motivation that you can see that, I mean, when we think about Earth or object, solid object, they break very frequently. It's not just because you drop your glass and it breaks, but also in nature you find, generally you find solids already in a fragmented shape. And this can happen because because there is some stress in the material, or a stress applied to the material, or the material itself is drying or freezing, which also can create stresses, and that breaks the solid. And here I just showed some example, which we also put in the paper, where you can see that actually something is built off from these fragments, and you can just study these fragments, how they look like, and just ask what kind of shapes you can observe. And basically this will be one of the main questions of my talk, is then when you fragment something, what kind of shapes you can observe, what kind of shapes you can observe in 2D and in 3D. And for that, these are the general, let me just go through some nice pictures. And because, as a physicist, when you do an excursion, you not only take nice pictures of some historic monuments, especially in a country. I visited Finland recently, before this research, and especially in a country where you hardly have any historic monument, but you take pictures of something which is interesting for a physicist, and these are fracture lines. These are my photos from this Suomenlinna, which is a fortress outside Helsinki. Basically, Helsinki was a garrison for this fortress. It was a tiny village some 100 years ago. But anyway, these fragments, these fracture lines, they look really nice. And in this granite, they look more or less straight lines, and they cross each other. So you can see that they make fragments, and you can see that these objects that are, objects which are surrounded by these fracture lines, they may fall out, and they form a kind of fragment. And you can see that this fracture line, they cross each other straight. So we have crossing, these crossing points, which look like an X, these X-shaped things. I took more photos, and you can already see that you always have this X-shaped thing, and you can see how these stones just fall out due to weathering. And you can always see that actually in this finished granite, these straight lines are really nice, very often very nice straight lines. You can really follow it. But now and then you can see that they do not follow, do not continue. I will talk more about this later. So there are fracture lines which end on another fracture line, and they are called secondary fracture line. So these objects, this fracture line initiated first, and then afterwards this big object just fractured once more. And that's how you can end up these secondary fracture lines. And when I thought that Mexico is a nice big country, so definitely I would find a picture with a nice fractured granite, and I did. It was, I hope I wrote the name correctly. It also looks nice. And here also what I found on this picture very nice is that you can see the structure the 3D structure which was taken out. So what you see is that there are rocks in which you have almost straight line straight fracture lines, and but actually if you just think, the whole thing fills the space. So it's a kind of question that, are they cubes which are there? So you can say that what fall out is what a cubic-like object, but we will come back to this question. But it's not always that simple. And if you, for example, think about mud, then it looks completely different. First of all, there are curved lines, but other than that, there are more of this secondary fracture lines, which end up in a T-like shape. Yeah? So you have more of that. And if we continue other mods, then you will end up situations where you have also in the previous one, these Y-like shapes. And this, Y-like shapes. And this is a basalt. In Hungary, I think we call it basalt organ. Everybody understands it. So you have these hexagonal shapes, and then the fracture line meet in a Y-shape junction. When we talk about this fragmentation process, you can think about in quite general sense. You don't have to stick to the stones. You can move away from physics, and you can move to the animal world or whatever you want. Even we will move to mathematics. And you can see that even animals can make very nice fracture lines, or then here I will call them mosaics. And also this one here, we can see it's more, here you have these Y-shaped junctions on this giraffe. And then actually we are back to some more physicist view or some mathematical view. When we want to characterize this kind of object, we found that there are three distinct junction types that describe this fracture line set that we see on the surface of this fractured object. We see this X-shaped, we see Y-shaped junctions, and we see this T-shaped junction. And we will see that they will be important. And actually this is well known for geologists, these kind of junctions, and they work well. And here we come to the research question that I want to ask. So my question is that what kind of patterns are there? So what are the possible set of patterns that we can see? So what kind of measures that you can measure and see? And can you tell that, for example, this measure has this available space? Can you just describe this? And also, what is the physical background of this cracking pattern? So can you create a physical model that links between the pattern and the physical background? So what is the difference? So for example, we saw that if there is a very solid object like rock and which is sheared, you see more straight line fracture lines. In a mud which shrinks, or in basalt which shrinks, you see more this hexagonal type figures. Can you establish a link between the background physics and observed pattern? Yeah. And but in order to do so, first we will focus on the patterns. Yeah. So that's why I showed you these images. So let's focus on the patterns. And when I talk about patterns, of course, these patterns look nice, but you have to characterize them, and we will restrict ourselves to certain patterns. And these are the assumptions that I will stick to, and that all the fragments are bounded by straight lines. So even though in the previous pictures you saw curved lines, I would really now straighten them if possible. And fragments are convex polygons. Okay? So convex polygons surrounded by straight lines. And the third is also very important, that the space is completely filled by these polygons. So there are no holes in the space. And first we will consider just 2D space. And the name of this in mathematics is mosaic or honeycomb. Even though you know the meaning of the honeycomb is the hexagonal pattern, mathematicians even use honeycomb also for non-hexagonal mosaics. And mosaics, it's very nice because we went back to the Greeks. We started with the Greeks, with Plato, the Platonic objects, and we started to fill the space with objects, and we went back to the Greeks with with mosaics. You can see that this is a nice mosaic, but actually not everything which looks like a mosaic is good for us. For example, this medieval stained glass won't be good for us because it's not convex. For example, this feet is not convex. But let's get back to business and measure quantities. And the quantities we decided to measure, which are these two quantities, are the number of edges of the polygons. So we said that actually the space is completely filled by these polygons, and we can always count the number of edges the polygons have. For example, this has 4 edges, this has 5, and we count the edges of these polygons, and we can characterize a mosaic with the average number of edges of the polygons. And we can also calculate the degree of the nodes. It's the same degree. I mean, you go there, here's a degree 4, here this has a degree 5. So you just count the number of edges that goes into a node and just average for the whole mosaic, and you have a number. And then start with something regular. Yeah. Actually, regular mosaics are the ones which have no T-junction. T-junction is the one when a node is at one side. Yeah. So what is possible? These Y junctions and X junctions, or slightly distorted X junctions. And if you consider, if you take a mathematical textbook, these are objects taken from a mathematical textbook, and you just measure these quantities, these are the points that you get. And as a physicist, you already see that, they may fall on a line, and indeed, it can be done. But before that, you can easily find the limiting cases as well. It's not so complicated. Because the smallest, I mean, you cannot have less than 3 sides for a polygon. And also, this is a Delaunay triangulation case when you have just triangles, and the other is the Voronoi tessellation, where in each node you have 3 lines entering that. Yeah, in one you fix v equals 3, and the other you fix n equals 3. And then with basic mathematical agreement, you can set the other 6. And actually, anyway, the 2 are dual to each other, so you can set it. This is how it looks like. There's a Poissonian Delaunay triangulation and Voronoi tessellation. But I don't know if you know that the Delaunay triangulation is simply if you have a set of points on a plane, and you just make triangles on it. And if you have, for example, a rectangle, you always draw the line, the diagonal, which is shorter than the other. Yeah, and so you construct a lattice, not a lattice, a triangulation. And a Voronoi tessellation is that you have nodes, and you consider the points which are closer to this point than to any other one, and that will create you a polygon. Yeah. And so for each point you will have a polygon, and you can easily show that these junction points will have always 3 connections. So these are the Voronoi tessellations. And if you want to go back to this equation, so you can see that these 3 and 6, these are the limiting cases that we just studied, but you can get the equation easily because you can calculate the angle between the lines. The average angle between 2 lines. Yeah? Now we are talking just about the average. In principle, at the right-hand side, you have, in average, n edges entering into this node. So you have this red angle will be 2 pi divided by n, average. And from basic mathematics, high school mathematics, you know the average, the angle of an V polygon. Yeah, V is the average. And then you just solve the equation for either for n or for V, and this is the line that you get. So everything falls nicely on this. So this already tells you that if you have a regular mosaic, the only possible place where your mosaic can have these average values, this n and v, are on this hyperbola. Yeah. So it's already restricts the possibilities that you can have for these 2 quantities. But actually that's, I told you already, this regular mosaics that excludes the T-shaped junctions, but in some mosaics in the definition which I allowed you for this mathematical definition for the mosaics, where I just wanted that it should be straight, bounded by straight lines or polygons and completely fill the space. These T-junctions are allowed. And this is a new junction. You have it also on a brick wall. I mean, this is the typical T-junction brick wall. This is the case when one side contains a vertex, and this is not one side contains a vertex. And you can also define a number to it. And but funnily, the mathematical definition of this is that how many polygons have this as an edge. And in this case, for example, n equals 3. And in brick wall case, it's n equal 2. And then you can have the new equation, which is where you have this p, which is the fraction of the regular vertices. So if it is 1, you get back the old equation. If it is 0, you get back the case of this brick wall. And then you can do this calculation. You can have images and do this calculation. We did a semi-automatized algorithm for that. And then I will show you shortly the results. But before we go there, let's study some cases. What happens? Let's go back to the case of the granite. When you have just straight lines, what it will give you? Yeah? When you have straight lines, first of all, it will be a regular mosaic because you have just X junctions. And you know that already the crossing point of two lines, so n will equals to 4. And then it will tell you that v also equals to 4. There is an other proof of that, but it's not so interesting. So if you take a piece of paper and you start to cut it with a scissor, and afterwards you consider all the fragments, all these small paper pieces that you cut it with the scissor, you cut it through again and through again, and afterward you count the number of sides the polygons have, the average, and you average up, it will be 4. Yeah, it's a mathematical certainty. And what happens if you start to introduce secondary cracks? So what means a secondary crack? So that if you take a fragment and you cut this small piece again, and you can easily show that it won't change anything, because if you have here an object and you cut it into half, you introduce actually 4 new nodes, yeah, here and here, and 4 new sides. So actually the average moves also towards to 4, 4. So whatever you do, I mean, if you just cut it everything by straight line, an arbitrary straight line, the average will be 4. So you will end up with a mosaic which has 4 on both P and V. Yeah. And actually, this model was used for as a known model for fragmentation. That when you have an object and then you cut the object in half with some probability, and you iterate this object this on, and then you get back the universal fragment size distribution as well. So this gives back the correct size distribution of the fragments that you see in, for example, explosions or whatever. And here is the space that I promised you, and I will spend a little time on this transparency. And this was the line that I showed you before. This is the regular mosaics, and this is a completely irregular mosaics. Yeah. This is the Delaunay case, and this is the Voronoi case. So this is the triangle, yeah, and the triangle, and here is the n equals 6, yeah, and the objects that I just showed you, this fragmented objects, this 10, 9, and 8, they are just here on the 4 line, yeah. The only difference is that actually while cutting them, the degree of the node decreases. Why? Because you introduce these T junctions, these irregular nodes, and that decreases this n number. So basically what you do is this 10 was the original cut, is the 4 by 4, and you just decrease and a little bit, but the average number of sides of the polygons remains just 4. And this is the all available space. But funnily, when we do objects, they are all in the upper phase. I will tell you about what. So we saw in the nature what we took as examples. We took basalt organs. This is mud. These are the tectonic plates. 15 is up here. These are permafrost, morphologies. This is also mud. This is the surface of a Hungarian mountain. And this is this 21, which is down here. This is a rock form from Finland. And we also put the mathematical stuff there. You can see the brick wall being here. So what we have is we have just objects up here, close to the Voronoi mosaic. So we don't see any Delaunay triangulation in the nature. Why? Because in order to have triangles, you need to cut your polygons at the corners. Yeah, so you have to start at the corner. And in nature, start something at the corner and cut always through the corner, it's very unlikely. So you will never have any objects here. And moreover, you can see that what's up here? It's 13, 14, 15, 13, 14, 15. I mean, mud, basalt, and tectonic plates. It's all something that cools down or dries out and it shrinks. Yeah? So this is something that if you shrink the objects, then you get Voronoi-like shapes. And when you have strong shear lines, then you end up with these primitive things and more of this granite and this rock case. And the question is that, can you somehow see that? Yeah, it just says what I've just told you, that actually we only see objects up here. And we see that hexagonal pattern is contraction of the material and cut lines is shear pattern. And actually what we did is we tested it in simulations. So what we did normal molecular dynamics simulations when we glued the particles together with small baking, small baked connectors, which could deform, but which could break based on some Tresca criterion. Yeah. And we put some strong viscous damping on the particles, and we had periodic boundary conditions. And that's what we observed. And this would be the Voronoi case. So what we did, we basically expanded the space. So it was difficult for us to contract that material, but if you extend the space, it's just the same. So what you see here, you have nicely this Y junction, and which is reminiscent to the Voronoi type of object. Yeah, we have almost exclusively this Y-shaped object, and basically all nodes, all vertices have a degree 3 in this case. And when we shear, we have failure lines. Yeah, you can see that they are all parallel to the boundaries. Unfortunately, this is due to the boundary conditions, they must be parallel to the boundaries. But actually, you can see that they are more at T or X-like. Yeah? So actually, you can see that if you want to have degrees or polygons with 4 sides, then you need to shear them. And if you want to have polygons with 6 sides, then you have to contract the space. And of course, you can get something in between. You just extract and shear, and you can have something in between. And this was basically our aim, and one of the research questions that can we predict. So what kind of mosaic you will see based on the stresses in the system? And our answer was yes. Not 100%, but you can have a good guess. So if the stresses are almost equal, and then you, it's very important that you contract the material or you pull on the material, then you will have this Voronoi-like mosaic, sorry. If you shear the material, it means that the sigma 1 and sigma 2 are not equal, or you just compress it widely, then you will have this quadratic shaped mosaic. Yeah, so that was the 2D case. And then our idea was that let's move to the 3D case. So this was more of a little bit of a game. Yeah, so it's really looking at nice images, do a easy simulation in 2D, and have a little bit of correspondence. But can this all brought to 3D and how it looks like? And the problem is that actually very little is known about 3D mosaics. The first problem is that it's very easy to see them, it's very easy to create them, and it's very easy to analyze them. Have experiments there. Yeah, in 2D it's very easy to have experiments. Actually, we found a set of just the regular mosaics. Yeah, it's just regular mosaics, and 3D regular mosaics. You see the points; they are taken from a textbook, a mathematical textbook. And first of all, you can observe that they don't fall on the same line. Yeah, so it was one single line for regular mosaics in 2D, but it's not anymore. It's still a thin object, though, but it's not a single line. And actually, we know that, we have already mathematical proofs for limits on this, but yeah, not much than that. And you can ask what happens. The primitive mosaic, if you cut the system with the planes, random planes, will result in cubic averages. I find it already strange. Yeah. So if you just cut the space with random planes, then you will have all kinds of objects. I will come back to this because we also measured it, but there is a mathematical proof for that. It's very easy. I mean, you just sit down, you just consider that at every point, 3 planes meet each other. This will create 8 objects. So in average, you will have a degree 8. And then you can easily prove that the average number of sides an object, a polyhedra will have, it will be also 8. So it's very easy to prove that in this case, you have an average of 8. And by the way, I find it really fascinating that you will have objects of different sizes, different shapes, and nodes with different degrees, but the average will be 8, not 8.00 something, it will be exactly 8. I find it already strange. And I just pointed to some specific things. Of course, it's very easy to take a 2D mosaic and make 3D out of it. You just have to include a third dimension. For example, this basalt organ as is here, and 3D Voronoi is 427. There is a discussion, by the way, that it's not 27, it's 27.03 or something like that. I'm not a mathematician, so I won't decide this question here. Yep. So this is the object where all possibilities. And our question was that what can you see in nature? So what are the objects which are possible in nature? And yeah, just test a little bit. And 3D observations. And actually, we were looking for objects in the space which could fit to actually the specific example, which were so easy to find in 2D. And actually, we ended up with one single specimen for a true 3D Voronoi. And it's called a septarian nodule, and it's an object. Actually, you can buy these things. Actually, this is also about the size of a normal egg, a little bit bigger, and you have to pay something like a few hundred euros for an object like that, depending on the quality. Yeah, around 100, sometimes 1,000 euros for a nice object, and it's very specific where they can form. They form deep in the ocean. Actually, because you already perhaps guessed from the previous one, you need stresses which are equal in all 3 directions. And it's very difficult to get. I mean, have the same stresses in 2 directions, it's fine, because if you have a pod that dries out, I mean, there are no differences between X and Y. But on Earth, there is always gravity, which makes the 3rd directions always different from the two other. So it's only in very specific places that you can find this. This hexagonal shape, we found them. These are basalt organs, but they are very not very widespread. I mean, you need a volcano for that, a specific one. And mostly all the examples that we found were looked like this. So, I mean, more of this cut by a straight line. And then the question was that, why is it so? And we went back to this nice simulation that we had, and that we did it in 3D. It's more expensive, of course, but I managed to do this. Oh, sorry. And that's what we got. This is the case when the stresses were equal. I'm just pulling on a space. It's also periodic. You can see, I mean, we tested, they were really nice, these Voronoi-like objects. If on two sides the stress was the same and it was 0 on the other one, you could have Voronoi-like patterns in one plane, and then just horizontal lines in the other one. It's like the basalt organ. And if we had this, shearing in all directions, you ended up with these cubes. And once again, in reality, it won't be that nice, but because periodic boundary conditions, just prescribe that all fraction lines should be parallel to the wall, so they are this perfect. And what we did, and we actually tried to map. So what we did, we run a lot of simulations, like a few hundred simulations with different stresses, and we just checked what will be the resulting object. Yeah? And it's difficult. I mean, we were struggling how to present them because we have three quantities that can have different signs, and because you can contract, you can push and pull on the materials, and actually we came up with this representation. Actually, we found Finn's curve of geologists, but they were not good for our purposes, because we wanted that a single point is a single experiment. Yeah, a single point prescribes what were the stresses in a system. And in this representation, mu is the ratio of the stress divided by the biggest one. So mu1 is the biggest one. But the problem with this one, that it is, you can have different signs on the sigma 1 and still have, overlapping. So actually you have two lives. One of them is for I, which is the sign of sigma 1, +1 and -1. And here I'm just showing the one when you are pulling on sigma 1. The sigma 1 is the largest stress is outwards, so you're pulling on the system with the largest stress. Because the other one, when you compactify, it's all blue. Blue is the primitive mosaic when you have a cubic shaped object. The green is this columnar mosaic, and the red is the Voronoi mosaic. And now, our interpretation of this was that you should mainly see blue one, because most of this is blue, and in nature, you will have all kinds of stress cases. But there is also some problem with this, that I don't know how many of you are doing molecular dynamic simulation. And the problem with molecular dynamic simulations that if you don't have too much time for this, and if you want to run a lot of simulations, then you have to make your particles soft. So actually, this was made with a particle which is as soft as rubber. Yeah, a little bit even softer than your rubber eraser gum. And if you make it stronger, then everything shrinks, and you will end up with just blue, basically, and just 2 points, 1 point red here, and this line being green. So what we found, actually, the message of this, that mainly in nature you should see actually this plane cuts by plane, and not these kind of objects. And now we see what it leads to. Yeah. So now we see that in nature mainly we see cut by planes, and then see what it gives you, what kind of result. And for that, because with this you can create. That was the maximum object, largest object that I could make. Even our largest computer, in Hungary, we don't have big supercomputers, unfortunately. So we went to a simple model where we cut a space with planes and just play around with this one. And I just, hopefully you will see this video. Actually, I like to tell the story that this is a very easy video. I just take a few planes and just interested in the fragments, yeah, in the objects in between. And you don't need anything which is beyond first year Bachelor of Physics. But actually, this was one of the most difficult codes I've ever written. Because I mean, it's easy to determine the crossing points, but already to determine this sides that are real sides of polygons and polyhedra, that was already not easy. And then to find the faces of the objects, that was even more difficult. And then the full, I mean, 3D polyhedra, to find really the polyhedra, this was my most difficult code that I've ever written. And I've already written, I mean, parallelized version of contact dynamics, but this simple, easy code was really. Sorry, I'm not an expert on visualization, but you can see that how these polygons look like. And I just would like to draw the attention that there are actually small, lot of small tetrahedra, and I will come back to this statement later. And actually what we did a cut model when we took a unit cube and just cut it with random planes, not that few, but more than this one. And the break model, when actually we took these fragments and we fragmented them further on with this model that I also used in 2D, that I just take the body and I take a plane and I cut it into two. Yeah, and how I did it, that bodies could break, and I put it into the aspect ratio, so if it was longer, it had high probability to break, and also the resulting parts could also break until a certain limit. So then we end up with objects. And why we did this? Because we have a nice mountain here in Budapest. It's just something like 5 kilometers from my home place, and also 5 kilometers from the university, so it's nice. Where you have these nice objects there, and it's very funny. So you have these fragments, and you can take them out by hand. Okay? So you can go there and just go there and by hand. You don't need any hammer at all. You can by hand take out fragments and measure whatever you want with them. And yeah, you know that actually the data published in the paper was, I mean, we also determined the shape was hand determined. So we have a very good technician who has a very good view in 3D. He scanned the stones and then tried to put a polygonal frame on top of it. Since then, we have a proper algorithm to do the same, but then it was handmade. I really appreciate those technicians who can do all these things by hand and really sometimes even more accurately than any algorithm would do that. And then here are the results, and I found them very interesting. And I will go through the images. The first figure is the number of planes we put in our model, and these are the averages, the V and the F. And you can see that they indeed converge to the cubic averages. Yeah, so the number of faces will go to 6, and the number of vertices goes to 8. So it's so nice we have cubic averages. But of course, we were interested in the distribution as well and compare it with the field data. And of course, we had to take into account certain features because when you do this identification, perhaps you don't recognize very nice small faces here and there. So we had to neglect very small faces and very tiny fragments. That was a problem that I told you that actually in the first experiment, the technicians were not careful enough and did not take that very tiny bit of fragments. So actually the average was a little bit higher than 6, but we repeated the experiment and now carefully taking any little fragment, and it was now a nice 6. So this is the faces. It should center around 6, and the break model, the cut model, and this red one as the field experiment. But what I find more striking is the number of vertices of these fragments, and it has this funny shape. And you can see that at even numbers, you have higher values than as odd numbers. Anyway, if it would be real fragments, like from the original shape, you shouldn't see any odd number. Why is it so? Because if you do the fragments by planes, I've already explained, at each junction, you have 3 planes, which cuts, which cuts the whole space 8 to 8 pieces at that point. And in this case, you can only end up with a so-called simple polyhedra. A simple polyhedra is a polyhedra where you have just, and every corner you have 3 edges. Yeah. If you have 4 edges in a corner, then there is something wrong. It's not a real fragment. Of course, when you do this analysis, you sometimes disregard it, and you will have 4. But anyway, if it's just 3, you can take the Euler equation, and you can show that you won't have any odd number of faces. But of course, because of this uncertainty, we put it into our model that you don't recognize very small faces, and we ended up with something which has the same characteristic as the field data. So actually, this was a kind of justification that indeed, when you think about fragments, they really have these cubic averages, and you can describe by this cut model. But I want to also draw your attention that actually this is just average. I mean, I already mentioned it in 2D that I find it funny that average is exactly 6 or 8 in the 2 cases, but it's a distribution. And also a curve, which I like very much, is that you can also determine which kind of polyhedra you found. Yeah? Now it's just for the cut and the break model. And this is also from a mathematical textbook. I really like this mathematical textbook. You have this polyhedra on pages and pages long, different ones. Maybe I think it's too small to see it, but this is the tetrahedron, and this is the trigonal prism, and this is the cube here. And this is an object which has also 6 faces and 8 vertices, but it doesn't have 6 rectangle faces. It has 2 triangle, this one and this one, 2 rectangle here and here, and 2 pentagon, 1 here and 1 in the bottom. And here you see the distribution, and you can see that actually the cube is nothing special. Yeah, you won't really find cubes. No, I think this 2 is more probable. I mean, also if you think about the cut model, you even see more tetrahedron than cube in the whole sample. Yeah? So you see more of this object, and you can also sometimes find very funny, very complicated objects, but nonetheless, the average will be always cubic. Yeah? It doesn't matter how you cut your space. And basically, this was the journey I wanted to take you. So actually, maybe I want so just to summarize. So this whole project started with just looking at nice images. I mean, as a physicist, you just look at fragments and just ask question that, I mean, can I predict this image? And the answer is, I mean, yes. I mean, if you know the stresses on the system, first of all, you can. When you do this mapping, you find out that. But if it's true, then I should mostly see just cubic fragments. Yeah? I want to see the straight lines. I mean, objects fragmented by planes and straight lines, and this will lead to cubic averages. And so if you count the fragments and the properties of the fragments, you should see cubic averages. And basically that was the message of our paper, and this is also the message of my talk. And I thank you very much for your attention. I try to find some nice mosaic, from wall mosaic from Mexico, and I really liked it. And this is from an old rain. And thank you very much for your attention.
Okay, thank you very much, János, for this very nice, very interesting talk. Are there questions, comments from the audience? Okay, János, maybe I start with a question. So I got a bit confused about the effects of human mankind in your results, because the last figure which you show here, this is these cubic shapes, they are built by humans, right? So
Yes,
this is,
yes.
no, and also in these photos from Finland, which you showed, where we have this cubic fragmentation.
Well,
does it depend that this wall is part of a construction, and the construction generates some specific stress and strain pattern? Which...
No, actually, in this, sorry, these finished patterns, they are natural. So they have nothing to do. I mean, this fortress sits on the top of it, and these are strokes here and there.
Okay.
So this is not the construction on the wall, it's just the rock on which this fortress sits. Yeah, because it's a very nice touristic destination. And there I didn't take photos of the fortress, but on the rocks. And that's how I found them. Okay. So they are natural fragments. They have nothing to do with blowing or something.
Okay. Okay, then a related question with the I think you commented this with the boundary conditions in your simulations. You always used rectangular shaped boxes to simulate these structures. Would it change when you use, let's say, a sphere, when you confine your particles in a sphere, and then you make pressure, homogeneous pressure? Well, you can also think on unhomogeneous, anisotropic pressure from the sides.
Yes, I mean, yes, but the problem was actually that, just going back, they are not far from here, that it's, I mean, Thomas, you did simulations. It's very tricky to do simulations with fragmentations. Here, the whole box was periodic, and it helped enormously, because then you don't have to, I mean, how you confine it, then you need something, I mean, for example, to a sphere and put pressure on it. You need to develop something special for that, or a rubber membrane, or something that puts the pressure on them, or some special constraint, which was not included in the code. And even if you do that, it's very difficult. Yeah, because, I mean, I tried to do with walls. Yeah, for example, it would have been nice to have walls which are not completely parallel, and it didn't work. I mean, it's too complicated. And the problem is that, you know, when one simulation runs for 2 weeks, you don't have too many shots. Yeah. And the problem with these things, that if you do it too small, then nothing ever happens. I mean, you cannot have a fragment which is 3 particle big.
How many particles are there in these?
600,000.
Okay, I see. And the interaction is just by friction, right?
Friction and this caking. That was, which was actually developed in Dewey's book.
I remember these figures.
Yeah.
Okay, there's a question from Gloria. Yep. Gloria, if you like.
Yeah, hi, thank you. Very nice talk. I'm just curious about one thing. Jupiter's moon, Europa, has these cracks on it, and it has one very particular crack that has an X shape. So do you think that one can infer from the X shape something about what lies below it? In other words, it is believed that underneath the ice there's water. So whether there's an X shape in one particular space or place. Can this tell you anything about the gradient in the water below it, or what would you infer from the X?
Yeah, I would infer the stresses. I would bet for a shear stress, and most probably you could even get, I think, so if you have a shear, I should be, but I'm not completely an expert on this, this fragmentation. I think for shearing something like this, you know everything. I think you even know the Green's function, so you can infer locally what the shape of a small crack would be. So if you have a point failure, then I think if you know the stresses, you will know the fragment. I mean the failure directions that you can easily calculate from the shear stresses.
But then but this only relies on the properties of the ice that conforms the outer surface, right? This
No,
does not...
I would more put on the water currents below. I would more bet
on the currents below.
Yeah.
Okay.
No, I'm not an expert. It's just a guess.
That's. I mean, I think everybody's in the same situation, but I was just curious. Thank you.
Yeah, my guess is that that it should be shear stress due to water currents underneath.
Good. Thank you.
Okay. Are there further questions, comments? So, if this is not the case, then thank you very much, János, for this very nice, very interesting talk. Yeah, and yeah, hope to see you soon again in person.
And the same applies to you.
Yeah.
And thank you very much for the invitation, and I was happy to present you this talk. And
yeah, very nice work. Okay, then see you next week. Oh, see you in 2 weeks. Next week we have Semana Santa or Eastern holidays here. So see you in 2 weeks for the next